Okay, Greg. So, in any of your science classes, you ever mixed vinegar and baking soda?
We haven't done.
You haven't done that? No. Have you ever done that at home?
Probably.
What happens when you do it?
It fizzes up a bunch.
It fizzes up a bunch. Okay. Let's do it. Okay. Got to wear your safety goggles. Can't do vinegar and baking soda without safety goggles.
Safety first.
All right. There's the baking soda. Yeah. Put a little dish soap in there to help it make bubbles, but there's baking soda's already in there. There's some vinegar. Pour them in there. Let's see what happens. Oh, there you go. Yeah, I had it all. It fizzes up, making bubbles. Go ahead and add it all. Where do the bubbles come from? Do you know?
Why would I know? I don't take your class.
You learned chemistry in 8th grade, right?
I learned molecules.
Okay. All right. So let's see what happens. What's baking soda made of? Look it up. Look at the box. What does it say? I think it's on the edge of the box. On the edge, not in the back. There you go. To the top. Ingredients.
Sodium bicarbonate.
Sodium bicarbonate.
Antacid.
Okay. Yeah, it's an antacid. Well, it's antacid. Well, what do you think vinegar is?
An acid.
Acid. So, what happens in this reaction?
A positive meets a negative.
Positive meets a negative. Great. So, yeah. So the acid protonates the bicarbonate and it makes carbonic acid. You know the molecular formula of carbonic acid?
No.
No? You don't? Well, what do you guys learn in 8th grade these days? H2CO3. Now, here's an interesting thing. If you think of H2CO3, it is what you get if you add H2O, you know what H2O is?
Mm-hmm.
And CO2.
Mm-hmm.
Now, what is CO2?
Carbon dioxide.
Okay, what do you know about carbon dioxide? Anything?
It has carbon in it.
It's carbonated. Good. It's an organic molecule. We're learning organic chemistry. What is the state of matter?
Well, it depends on the temperature.
There you go. At room temperature, what is the state of matter?
Gas.
CO2 is a gas at room temperature, right? So in this reaction, sodium bicarbonate has been protonated to make carbonic acid, but then it falls apart into H2O and CO2. So what do you think the gas is inside the bubbles?
CO2.
CO2. That's exactly it. So that's what happens when you mix baking soda and vinegar.
You had to add the dish soap. So
I add the dish soap to make the bubbles look bigger. Actually, if you do it right, you can get really big bubbles. I didn't do it right, but yeah. But you still, it gives off gas, right?
Mm-hmm.
And that gas is CO2 because the decomposition, H2CO3, carbonic acid, decomposes into water and CO2. So that's baking soda and vinegar. Okay, so let's explore this chemistry of carbonic acid that we formed in our reaction of baking soda and vinegar. So carbonic acid is an acid, which means it can proton transfer onto bases, something like water. And in fact, the pKa of carbonic acid is 3.6, which means that the equilibrium constant for the reaction of carbonic acid with water is 10 to the minus 3.6. What it also means is that the reverse process, the reaction of bicarbonate with acid, has an equilibrium constant of 10 to the positive 3.6, so almost 10,000. So it's very favorable in that direction, which is why we, when we do the reaction of bicarbonate with vinegar, we get the formation of carbonic acid. But of course, the problem is that carbonic acid doesn't hang around. It falls apart into CO2 and water. And so that's what we see in our demonstration, that it falls apart into carbon dioxide and water. And as Greg correctly surmised, that the bubbles contain CO2. you can't tell it from the demo, but this reaction is technically, or in terms of chemistry, is actually fairly slow. If it was faster, you'd have like an explosion. So think about, things that go a lot faster, they end up being explosive. This is a really nice reaction, which means it makes a really good demo, and that's why it works so well. So it makes a really good demo to do. It's a relative because it's such a relatively slow reaction. But if that reaction is slow, that means that the reverse reaction, carbon dioxide plus water going out, starting here and going that way, is super slow. And so this is a really, really slow process. It's not easy to turn carbon dioxide and water into hydronium ion and bicarbonate. But the body does that. And the way it does that is it catalyzes this reaction using an enzyme. And that enzyme, which is Ca carbonic anhydrase, we'll talk about in a little bit, that makes that reaction really, really fast. This reaction in the presence of carbonic anhydrase, carbon dioxide with water, leading to the formation of hydronium ion and baking soda, your body uses that all the time in order to regulate the pH of the blood. This is how it keeps the pH of the blood in the right place using this reaction, and it's all based on the fact that we can use carbonic anhydrase as a catalyst. So, in summary, carbonic anhydrase is used by the body to regulate the amount of carbonic acid, and ultimately, because carbonic acid dissociates into hydronium ion and bicarbonate, it controls your amount of bicarbonate in your blood. So carbonic acid is very key for that whole thing. But there's a consequence of that, and has to do with the role of carbon dioxide in fizzy drinks. And so there's a paper published not too long ago that looked at what happens if you block the activity of carbonic anhydrase, okay? If you block the activity of carbonic anhydrase, beer, for example, tastes like dishwater, and other carbonated beverages, the participants described their taste as being flat. So even though it's carbonated, it tastes flat, so you don't taste the carbonation. Why is that? Well, if you think about it, you used to think that the reason things tasted carbonated was the effect of gas and the dissolved gas in the liquid, affecting your mouth and stuff like that. What's proposed in this study is that the bite of carbonated beverages is not due to the fact that CO2 is a gas. It's due to the fact that in your mouth, carbon dioxide reacts with water in the presence of carbonic anhydrase to lead to the formation of carbonic acid. And so it's the carbonic acid in your mouth that's actually burning your mouth and your tongue, and that's what leads to this bite and the fizziness that you have in drinks. So it's the amount of CO2 that's in the drink that leads to more the formation of this carbonic acid. So this always makes me think about when I was growing up. There was a commercial for Barq's root beer, and it was always the tagline that they used was that Barq's got sparks. And here you can see it over here, that Barq's has bite. And it was supposed to be that Barq's root beer had a more carbonated feel to your mouth. And I just assumed that it was because, there's more CO2 and everything like that. And the reason Barq's has that sparks that's associated with it, I figured it out a few years ago. It's because they overcarbonate it. So they extra carbonate it, which leads to more formation of carbonic acid in your mouth, and more formation of carbonic acid in your mouth means a bigger bite, or the sparks that you have from root beer. And the reason I figured this out is, like, if you pour Barq's into a glass and let it fizz a lot and have a big head on top of it and everything like that, and let that go down, even after you do that, it's still very, very carbonated. If you do that with a regular root beer, it goes flat, but Barq's doesn't go flat if you do that, and because it's overcarbonated. So that's my assessment of it. But there's an important consequence of this, is that you can feel the effect of this carbonic acid in your mouth, and that has led to this idea and this observation that when you drink a carbonated beverage, it's very refreshing, and you feel that way. But you know what? This is carbonic acid there. And what happens when you put acid and hold it in your mouth for a very long time? It starts to do the things that acids do. What we're going to do, and the last part of this is you're going to see what we used to call, what we friends and I call a Coke-Tongue Challenge. We're going to do it without Coke, but it's still going to work. And we're going to do the Coke-Tongue Challenge to see how long can you stick your tongue in a carbonated beverage before it becomes too painful and you have to stop. Enjoy this little activity that my kids and I did together.
Okay, so Greg, we learned that when you mix baking soda and vinegar together, it forms carbonic acid, and that falls apart to make carbon dioxide and water, right? Now, what happens when you drink carbonated beverage is it goes the other way. You take carbon dioxide and water, and they come together to make carbonic acid, and that's by using an enzyme known as carbonic anhydrase helps that happen. So what happens when you drink the carbonated beverage, the carbon dioxide reacts with water in the presence of carbonic anhydrase, and it leads to carbonic acid. Now, what do we know about acids?
It hurts.
It hurts. And so the reason these drinks, fizzy drinks, you can feel them on your tongue is because you're getting the feeling of carbonic acid eating at your tongue, okay? It hurts. You know, when you usually drink these carbonated beverages, you get this tingle feel in your mouth. That's the beginning of it. But what happens if you keep your tongue stuck in that acid over time? It actually gets to be very painful. And so my friends and I, when we go to conferences, we have what we call the Coke-Tongue Challenge. We're not going to use Coke today. We're going to use Orange Crush, but good enough. Any carbonated beverage. And your challenge is how long can you stick your tongue in carbonated beverage before it hurts and you have to give up. Okay, guys? So we're ready to go on this. Now, we have to be really careful when we do this. And so I'm going to do it because it's really easy to cheat in this. If you just pour it out and it foams up and everything like that, you lose all the carbon dioxide in your drink. We don't want to do that. We want to actually pour it very softly so that it doesn't get all fizzy and it doesn't lose the carbon dioxide. So I'm going to try to pour it slowly. Crush. I think we're going to make it. And that should be it. Okay. You ready, guys?
Yep.
We're going to stick our tongues into the Orange Crush and see how long we can keep it. 1, 2, 3, go. I'm going to quit. These guys are going to keep going. My tongue is numb right now because these guys just wanted to, now they're challenging each other to see who can last longer. Trust me, that's painful. Boy, does that hurt after a while. Now, what's going to happen is that they're going to be there so long that it's going to get better. But if they kind of wiggle their tongue around and mix it up a little bit, it might get a little bit worse. And so we have to stir it up. If we put a stir bar in there and everything like that to keep it stirred, but then you don't want to stir it too much. We'll call it a tie. Okay, guys, give it up. Did that hurt?
Yes. A little bit, yeah.
A little bit, yeah. That's a very painful experience. But it's because of carbonic anhydrase catalyzing the formation of carbonic acid from carbon dioxide and water. And a great example of organic chemistry in real life.